And I'll send one more reminder in the collaboration Slack channel just in case.
Mm-hmm.
So where were you before coming to Stony Brook?
I was at Saclay.
Okay.
I was working with Eric Permeter there.
Nice, nice.
Um,
So are you used to Stony Brook by now, or is it still still an adjustment?
It's kind of still new. I mean, also the department is a bit different from. So I was in the strings group in Saclay, and here I'm in the nuclear theory group. So the field is slightly different for me. So
Yeah, it would be different, yes. But do you have a chance to sort of interact regularly with the particle theory people in
uh,
Stony Brook?
I'm actually spending time in Brookhaven National Lab also significantly, like
Oh, I
3 days.
see. Okay.
So 3 days a week is kind of yeah, like the 3 days in Brookhaven, 2 days in Stony Brooks, somewhere like that.
I see.
So since I've been working with Raju also kind of lately, so I still haven't like yeah, so I still have to find some common equilibrium.
Okay. Yeah, no, because I figured based on I remember looking at your papers, and I would guess that you would have a fair bit of overlap with some people in the group as well. Yeah. So usually the people come in, a couple of minutes after the official start time. So
Right, that's correct.
wait another couple of minutes and then begin.
Mm-hmm.
Okay, well, we're at 11:02 Eastern, so maybe we should start. And then people will connect. So today we're very lucky to have Himanshu, who's a member of our collaboration, actually, who started working with Roger recently, and will tell us about some exciting things about energy scattering in QCD and gravity. So go for it, Himanshu.
Thank you so much, Alexi. Thank you so much once again for giving me this opportunity to speak about my work. So I'll be talking about some work that I've been doing with Professor Raju Venugopalan at Brookhaven National Lab. And as the title of my talk suggests, this work is about uncovering some common some common universal features that appear in QCD and in gravity in the high energy asymptotics. And as we'll see later on in the talk, its connection to shock waves and the role it plays. So the starting point is this observation that perturbative QCD and perturbative gravity have a common have a very strong analytical connection between the two, and this was made concrete by this work of Byrne, Carasso, and Johansson. And there has been tremendous progress in understanding these interconnections in terms of the perturbative scattering amplitudes in both the theories. So to be slightly more concrete, this relation, which goes under the name of the BCJ double copy, states that Yang-Mills amplitudes can be mapped to their gravitational counterparts by applying a simple set of well-defined color to kinematic replacement rules. And as to why this mapping works, a partial answer lies within string theory. And it goes back to the work of Kawai, Levin, and Tai, who pointed out that the tree-level closed tree-level closed string amplitudes can be written in terms of tree-level open string amplitudes. And once you take the field theory limit of these amplitudes, you get a mapping between perturbative QCD and perturbative gravity. Today, our interest would be to look at QCD, first of all, at high energies, specifically in the high occupancy limit. So just to explain the idea a bit further. So here I imagine that there is some hadron with it could be a pion, it could be a proton with some valence quarks, and you boost it close to the speed of light. So the three lines that I show here are their world lines. So at very high energies, these valence quarks will be at very, very high rapidity, and they will start sourcing gluons of slightly lesser rapidity. And these gluons will start to slowly take up the phase space which is provided by the size of the hadron. And since the process is happening at extremely high energies, these emitted gluons are also at relatively high rapidities, and they internally become source of further slightly lower rapidity gluons. And in this manner, there's a cascade of partons, which ultimately leads to a system of very high occupancy, which is characterized by some integer n, such that the integer n times the coupling of the problem, which here is alpha strong, is of the order 1. So this is what one would refer to as a system of high occupancy in QCD, and it goes under the name of color glass condensate. And there's a very nice review by Iancu and Raju from several years ago that one can take a look at. So this is the setup in the QCD side. And the question that we are asking is that if you take the high energy limit of gravity, there is a similar high occupancy domain in gravity, which is populated by black holes. So you can view black holes as some high occupancy state of gravitons in this case. And a concrete question one can ask is there a similar color to kinematic, or not necessarily color to kinematic, but any relation between QCD at high occupancy and gravity at high occupancy, which is of the BCJ type. So does such a relationship exist in the high occupancy domain or not? So this is the question that we posed in our work. And the question, and another question is, if such a double copy exists, then what is precise structure? Is it similar to the BCJ, or if it's different, then in what ways is it different? So having an understanding of such a double copy relationship between QCD and gravity at high occupancy would also have applications, for instance, in gravitational radiation at high in Transplanckian scattering, and also for the interesting question of black hole formations at small enough impact parameters. So with that motivation, here's the overview of my talk. So we will begin by looking at the multi-radial limit of QCD and gravity for 2 to n amplitudes. So the reason that we have 2 to n is because we want to create a situation where there is a large occupancy in the final state. And we will see the connection of these theories in the multi-radial limit by looking at by establishing a connection of such processes to classical physics, in particular the connection to shock waves. We will show that for like a particular 2 to n, so this 2 to n process can be broken down into sub processes, and the simplest one among those would be 2 to 3 in the multi-radial limit. And we will recover some of the explicit formulas that one can get from 2 to 3 amplitude-based computations by a purely classical considerations, in this case, a Shockwave collision. And we will find some double copy relations between QCD and gravity for this kind of processes. And finally, I will conclude by giving some speculation for what kind of implication does these findings will have on the gravitational radiation spectrum and black hole formation in high energy scattering. So if there are any questions. Okay, very good. So let's begin. So in the QCD side, so the QCD in the radial limit, so first we look at some 2 to 2 amplitude. So here I'm agnostic about the nature of the external particles. All I'm specifying right now are their momenta. So P1, P2, P3, and P4 label the momentas of the external particles. The Mandelstam, the center of mass Mandelstam variables defined as the sum of the incoming momentum P1 plus P2 squared. And the momentum transfer T is defined as the difference of P1 and P3 squared. And so the radial limit is defined as the one where the center of mass energy is much greater than the momentum transfer, which we take to be also much greater than lambda's QCD. We do this because we want to work in a regime where perturbative QCD is still valid, so that we can make we can do some computations. So this kinematics is can be also understood as a strong ordering in the light cone momenta of these particles. So of the final state particles. So this inequality here is the same as a large plus like P3 plus component for one of the particles as compared to P4 plus. So this parameterization this inequality here can be further written in terms of what is called the rapidity, which is just a way to parameterize light cone momentas. And this inequality here is the same as the inequality that the rapidity of these momentas P3 of P3 and P4 are strongly ordered in this way. So the reason we introduce these rapidity is because when we go to a 2 to n frame process where we have instead of radial kinematics, the multi-radial kinematics, the relevant kinematic regime is defined as the one where there is a strong ordering in the rapidity of all these final state particles. So the rapidity of so y0 is the rapidity of one of the external particles P3, and yn plus 1 is for P4, and there are on top of those two there are n further for final state particles. So this is the kinematic regime which gives the dominant contribution to 2 to n multiparticle production amplitude. So QCD in the multi-radial limit can be so one can do computations in this limit using the framework of perturbative QCD, and this gives a systematic procedure to extract the leading behavior of each amplitude and summing those contributions. In the so-called leading logarithmic approximation, so this is an approximation where one resums terms which are of this type, where we have alpha s log t over s, which is of the order 1. So one has to resum all the pieces in the Feynman diagram, in various Feynman diagrams that have this particular behavior. And in this leading log approximation, the cross sections are described by the BFKL evolution equation, which is a Hamiltonian evolution that is governed by this BFKL kernel K. For the next few minutes, I will try to describe what this kernel is, what are the main building blocks of this kernel. So we have a situation, we have a 2 to n scattering amplitude, in which we have, in the final state, we have particles which are strongly ordered in rapidity. So in this ladder, there are two main building blocks. The first one is the regized gluon propagators, which connect the different rungs of the ladder. And the second is the effective emission vertex, which are famously known as the Lipatov vertex. So these are some non-local vertices that controls the emission of these final state particles. So the regized gluon is essentially a resummation of all the leading log s over t contributions of a sum over exchange of this type. So in the Ricci asymptotics, one can resum all this in infinite contribution in this entire infinite series. One can extract the leading alpha t log s pieces which are sitting inside these amplitudes, and a resummation of that entire series gives effectively rise to replacing basically this in a single propagator 1 over t to 1 over t times s over t to the alpha. This exponent alpha is called the Ricci trajectory, and at one loop, its expression is infrared divergent, and it takes this particular form. When we typically write down 2 to n amplitudes, it is often the norm to rewrite this factor in terms of the rapidity. So instead of 1 over t, we have e to the power the Ricci trajectory times the rapidity of times the rapidity difference of the two particles which are in the final state. So this is for the regized gluon propagator. The second building block was the Lipatov vertex. So this Lipatov vertex is an effective vertex, which is a sum of these 5 different Feynman diagrams. So this corresponds to an emission from. So the 4 of these diagrams correspond to an emission from the external legs before and after the collision, and from both these particles, and a 5th one that corresponds to an emission from the center. So using Jacobi color identity so this computation is again in the multi-Ricci kinematics. So one can add up the contribution of these diagrams and find that effectively one can just replace the sum of these diagrams with a single diagram that has an effective emission vertex, which takes this particular form. So this vertex is gauge invariant, and further, meaning that when you replace like the polarization tensor of this emitted gluon with its momentum, then the contraction with CMU vanishes. So putting these two ingredients together, so here I'm representing this amplitudes with all its bells and whistles. So we have some initial state momenta P1 with some color index A1 and so on and so forth for the for every single particle that appears in this amplitude. So this 2 to n amplitude, the building block is basically these vertices and these the regized gluon propagators that I showed you, and we just sandwich them all together in this particular manner, and we get this particular amplitude. One can use this amplitude to further, for instance, compute the total cross section for a 2 to 2 process using optical theorem. So we have like 2 of these amplitudes, this one and its dagger, and integrated over the phase space factors, and one finds that this amplitude has a rising cross section. So going from here to here is some work, and it's a straightforward calculation that is explained very beautifully in this review from 95, and one finds this particular behavior which is there in the BFKL dynamics. So BFKL basically predicts that that cross sections in the Regge asymptotics violate the sacred force are bound, and this basically means that BFKL cannot be the full story. So we'll come back to this point later in the talk. So for all what I need for this particular presentation, this is what we will need for QCD. So now let me change subject a bit and move to gravity. So in gravity, the situation is different. So instead of
could you say again? So what unitarizes this amplitude?
Yeah, so I didn't say it, but it will come later. So the point is that in the BFKL evolution, there is no so the non-linearities are not taken into account. So just to go back to this very heuristic picture, so after a certain point, these so the BFKL evolution is the one where the gluons are just emitting. There is no like absorption of the emitted gluons. So in a sense, the BFKL evolution is completely linear in the sense that this parton cascade is infinite, but that cannot. But that cannot be the case, because at certain point there will be overlap in the phase space density, and the gluons will start recombining. So they will undergo recombination, and that recombination process is not captured by BFKL. So this is to unitarize the BFKL amplitude, one has to go beyond the approximations which are made in BFKL. And that goes under the name of Belitsky-Kovchakov equation that I will describe later on.
Okay.
Right. So in the gravity in the gravity side, the situation is a bit different. So let's first look at the 2-to-2 scattering. So at large enough impact parameters, but by large enough I mean an impact parameter which is greater than the characteristic length scale of the problem, which is fixed by the Schwarzschild radius, RS, which in turn is fixed in terms of the only dimension full scale in the problem, which is Newton's constant, and the center of mass energy. So when B is much greater than RS, it is well known in gravity that the 2-to-2 amplitude simply iconalizes. So in QCD we saw that this resummation gives rise to gluon regization, but in gravity the leading effect of resumming this entire series is essentially an exponentiation of the amplitude of the Born amplitude in the impact parameter space. This has been a well-known fact, which was first observed in this work by Muzinich and Soldate, and later on by Kabat and Ortiz. And furthermore, in the context of string scattering by Amati, Ciafnoni, and Veneziano. So as I already said, so as opposed to QCD, graviton regization is kinematically suppressed as a T over RS, which for small enough, which for B much greater than RS is roughly the same as RS over B squared. Now, there's a very neat way to see why graviton regization is kinematically suppressed. So a one-loop calculation in both in QCD and gravity reveals that there are terms in the one-loop amplitude where one finds that in the QCD side, there is a term that goes like I pi TS, where TS is the square of the color factors T1 and T2 associated with the two incoming color like charged colored particles. And there's another term that is TT squared. So TT is the difference between T1 and T3 squared. So these two like colored Mandel-Stamps are they're the analogs of the momentum space Mandel-Stamps, TNS. So that's why the subscript S and T. So there's a term that goes like I pi TS squared, and there's another term that goes like TT squared log S over T. So in the Regge limit, the term that dominates in QCD is this log S term. Now, one can do a very similar calculation in gravity, and one finds that there are like a clean analog of these terms, which is I pi S. So you replace essentially T sub T squared with the center of mass energy, and T sub T squared with the momentum transfer. And here one finds that when you take the Regge limit of this answer, the term that dominates is this iconal phase term. So this is like our first encounter in this talk of this color kinematic of this implication of sort of the color kinematic replacement that quantitatively changes the behavior of scattering amplitudes in the Regge limit in QCD and gravity. So this was so this situation is has been known and is certainly true for large impact parameters. But as one lowers the impact parameter, as soon as one is sensitive to the processes where RS over B is of the order 1, then or actually even much before that, one cannot be ignorant about these contributions. And one has to take into account the fact that graviton regization, which although is kinematically suppressed, it still undergoes regization because of the presence of this kind of term here. And the one-loop graviton Regge trajectory was computed by Lipatov in a paper from 1982, and he found that as opposed to QCD, the Regge trajectory goes linearly with the Mandel-Stamp T. So this feature is also there in gravity, although it's kinematically suppressed at large impact parameters. The second feature in gravity, which is again the analog of QCD, is the analog of the central emission vertex, which we will call the gravitational Lipatov vertex. And the effect of this term is also at subleading order in RS over B expansion. So this term, this effective vertex was initially computed by Lipatov, where he argued for a structure which is very similar to like a double copy of the QCD Lipatov vertex. So this gravitational Lipatov vertex, essentially you take two such QCD Lipatov vertices and you just club them together in this manner. Now it turns out that when you construct an amplitude which is of which is a bilinear of two copies of the QCD Lipatov vertex, there are terms in this amplitude that is which will have simultaneous overlapping poles in two different Mandel-Stamp variables. Now, such poles cannot be present in a unitary amplitude. And because of that, what Lipatov did in his original paper was to introduce a term of this sort, two copies of n mu, and n mu takes this particular form. So this is of the form of a soft photon factor. And the role in life of this particular term is to cancel these simultaneous overlapping poles that you get from C mu, C nu. So in the original paper, Lipatov didn't give any further like constructive proof of the appearance of this term. It was, at least to my understanding, this was just based on, the argument was just based on the absence of the demand that the overlapping poles should not be present. Now, so with these two building blocks, one can just go ahead and construct the 2 to n ladder in gravity in exactly the same way as was done in QCD. Now, before I move on, I just want to make first an interlude and make connection to shock waves and where do they appear. So if we have like a generic Feynman diagram where one of the external lines is a high energy line, one can show that the way this high energy line would interact with the rest of the Feynman diagram would be by some n iconized exchanges. It will be an iconized exchange because since the external line is at very high energies, the momentum transfer, the change in the momentum of these internal high energy propagators would be very small, and one can just replace them with iconized propagators. So one can show, and this was shown by Akuri and Saotome, that the effect of this high energy line is simply to replace it with an external field, and this external field takes the form of a shock wave. So this picture is true both for in QCD and in gravity. And this was shown like in the perturbative description where we have like an iconized exchanges. More like in a more dense setup, for instance, when we have some more complicated deep inelastic process where one scatters some dipole of a nucleus. So this a nucleon is supposed to denote some sort of valence quarks, which at high energies will give rise to these gluons of slightly less rapidity, and this whole blob will constitute the nucleus. So this was a picture I showed in the beginning of the talk, where we have to start with some configuration of color, which when one boosts to the speed of light, one gets to the state of matter, which is called the color glass condensate. So the point here I'm trying to make is that when we boost this configuration of matter to the speed of light, what one gets at the end of the day is some sheet with a transverse profile, which to start with some smooth function of the transverse coordinates, and it moves in the x plus direction while sitting at x minus equals to 0. So one can model this particular part of the Feynman diagram, just like we saw in the previous slide, with a shock wave. And to be more concrete, this shock wave is sourced by this this color current, which is a covalently conserved current that is given by G times delta of x minus times this transverse density rho of x times the scalar factor dA. Given this particular profile for the color, one can ask the question, what do the shock wave actually look like? So the thing is that if you plug this equation into the Yang-Mills equations of motion, one gets an exact solution to the full nonlinear equations of motion, and it takes this particular form. Just to give one curious property of these gluon shock waves, so when we write the shock wave in this particular form, it is kind of trivial to see that for x minus positive and x minus negative, one gets the vacuum, but at x equals to, and all the field strength is sitting at x equals to 0. However, the vacuum that one gets on the either sides is not the same vacuum. They are even though the field strength vanishes on either sides, they are still like different vacuums, and they are connected to each other by a pure gauge transformation. So there exists a gauge transformation where it is possible to show that the field configuration AI takes the step function form. So for x minus, which is positive, this is a pure gauge, and thus the field strength vanishes. But for x minus is negative, this is just a equals 0 vacuum. There's an analogous story also in the gravitation in the gravity side. So in the gravity side, if you take a Schwarzschild black hole and boost it to the speed of light, what one gets is the Eiselberg-Schwarzschild shockwave metric. And here one starts with some black hole of mass m, but when one takes the relativistic limit, one has to take them in a manner such that the mass of the black hole goes to 0 as one takes this gamma factor, the Lorentz boost gamma factor to infinity, such that this combination is held fixed. So in this process, one develops a stress tensor, and the stress tensor is again of the same form as that of the gluon shockwave. And one can again plug just in exact same analogy as in QCD. One finds that this stress tensor is completely solved by the full nonlinear Einstein's equations of motion by a metric of this form. And in exactly the same way as in QCD, the curvature of the space-time produced by the shockwave vanishes for x minus and x positive and negative, but the vacuum is not the same. And one can see this by doing a coordinate transformation where the metric takes this particular form. Although this metric looks kind of horrible and complicated, if you plug this into Mathematica and solve it for y minus positive, well, you will see that the Christoffel connections are non-vanishing, but the Riemann, all the components of the Riemann tensor vanishes. So if you have like clocks and meter sticks on either sides, you will find that you are measuring different times and distances, which is the effect of the gravitational shockwave passing by, but the curvature in the both sides will be zero. Now, so here is our first concrete color kinematic correspondence between these two classical shock configurations. So it was shown by Akuri and Saotome that if you take the gluon shockwave and write it in some covariant form where the momentas, so in the previous slides, I showed the expression for some fixed component of the gauge field, but if you write it covariantly, it takes some particular form. And here I'm writing things in terms of momentum in the momentum space. So I did a Fourier transform in the transverse coordinates. So what Akuri and Saotome found that if you take this particular, if you look at this particular part of the gluon shockwave answer, and you do the replacement where you send the color factors to I times some kinematic factor Q mu. So just introduce another copy of that. And what one finds is an answer for the gravitational shockwave. And so here I'm showing the expression for just the static high energy configurations where we have just a single shockwave. Towards the end of the talk, I will show that when you collide two such shockwaves to each other, the radiation which is produced in such a collision process also obeys a double copy relation where one encounters such a replacement rule. Please hold on to that. So with that, let's look at the problem of gluon shockwave scattering. So as I discussed earlier, the collision of two nuclei at sufficient high energies can be approximated by essentially collision of two gluon shockwaves. So here I'm showing a space-time diagram of the collision of two such shockwaves. So on the X plus light cone, we have a shockwave which is generated by this transverse density rho A. And on the X minus light cone, I have the shockwave which is generated by this transverse density rho B. And before the collision, we have the Minkowski vacuum. And just after the collision, we'll start generating radiation in this region 4. Region 2 and 3 are these pure gauges, which I discussed a few slides ago, which is the region of vanishing curvature. So in this classical problem of radiation produced in gluon shockwave collisions, it turns out that one can show that the emission of gluons that appear here are precisely dictated by the Lipatow vertex, which one found through amplitudes computation in the multi-regi kinematics. And this calculation can be done purely using classical Yang-Mills equations of motion, and these ideas were initially discussed in these papers. where one just treated the problem completely classically. Just to briefly outline, so we have two incoming sources along the light cone X minus and X plus. And as I said earlier, they are dictated by these transverse sources, rho A and rho B. One can do an approximation where rho A is heavy and rho B is light, solve for the background first, whose solution we already know, and then do a small perturbation around the background, which is this small a mu, which corresponds to the field generated by this light source. The perturbation a mu can further be decomposed into a term that contains a factor of rho b, which is the source for the other shock, and a term which is of the linear, which is of first order in rho a and first order in rho b. So this is the term that will correspond to radiation at the end of the day. So one can do the simple exercise of linearizing the Einstein's equation, and one has to first fix some gauge in order to do that. So the simplest choice is the light cone gauge, where one sets a plus equals to 0. And what one finds at the end of the day is that the linearized Yang-Mills equations take this particular form, and the leading order solution has some dependence on rho b, plus a term that goes like order rho A and rho B. So this is the term that is important for us, and which contains the radiation field. Yeah. Is it a question? Yeah. To solve for this radiation field, what one does is that one takes the Eikenel approximation, where the source J plus is evolved, but all the other components of the current are turned off. So in the Eikenel approximation, the only component of the current that will be relevant for the process is J plus. And this evolution of J plus can be done using the covariant current conservation equation, and it leads to certain expression. So once you have the expression for the evolved J plus, you plug that back into the Yang-Mills equations of motion, and perturbatively one can solve this equation. And from this analysis, one finds that the solution for the radiative space-time takes this particular form. So first of all, there is a pole in 1 over k plus and 1 over k squared. This is the pole associated to the emitted gluon. And then there's the central emission vertex, which is exactly the same as the Lipatov vertex. So one just by doing this purely classical analysis, one finds the emergence of this Lipatov vertex. And they couple to the sources rho A and rho B, and the propagators Q1 squared and Q2 squared. This calculation that I showed here was in the so-called dilute approximation, where the source rho A and rho B were treated only to the leading order, to the first orders itself. But it turns out that in QCD, one can also generalize this calculation to the so-called dilute dense approximation, where one of the sources of the shock wave, say rho A, is kept to all orders, but the other source, rho B, is kept only to linear order. And in this calculation, the only difference with respect to the dilute calculation is that the effect of keeping all order terms in rho A is essentially to resum them into a light-like Wilson line operator. So this rho A is resummed into this U operator, which is just a path-ordered exponential of the background gauge field, which is generated by this dense shock wave. And pictorially, the meaning of such an approximation is to essentially keep all the multiple scattering effects of them of the dense source rho A with that of the emitted gluon. So this is formally this is a process which will dictate an emission of a gluon which is of a very high frequency. which will interact with one of the sources multiple number of times. So in the remaining of the talk, I will discuss how one can kind of repeat this entire exercise in the gravity side and find that the gravitational Lipato vortex can also be recovered in exactly the same way by using just classical Einstein's equation coupled to these shockwave sources. So in the gravity side, one has this energy momentum tensor, which have these two. The initial energy momentum tensor consists of these two shockwave sources, rho h and rho l, and what one does is to treat one of the sources as heavy and the other as light, and solve for the metric by expanding around some background value, which is fixed by the heavy shock wave. And one can linearize the Einstein's equations of motion just like in the way one did in QCD, and set up the linearized Einstein's equations. The first kind of departure that one finds in the gravity side is that the Eikenal approximation is not consistent, meaning that if you just kept terms in the Einstein's in the energy momentum tensor, which are just initial so here the components of the energy momentum tensor which were turned on were T minus minus and T plus plus. It so happens that when you analyze the Einstein's equations, there will be components of the energy momentum tensor which will have legs along the transverse directions which are turned on, and you need to turn them on for consistency. Otherwise, one gets a non-inconsistent set of equations. So this is the first departure from QCD. Once we have, but the problem is how do we determine these components of the energy momentum tensor? Because there are more components than there are conservation laws available, because the covariant conservation equation is just 4 equations, but there are much more components that appear on the right-hand side of the Einstein's equation. So what one needs to do is to come up with a theory of sources, which for simplicity, one can just take to be point particles. Which means that to the Einstein's action, one just adds an action of a massless point particle, and whose energy momentum tensor is given in this manner. So then the problem breaks down to solving for geodesic motion of this particle in the background of a shock wave, and this is and that geodesic is a null geodesic which one can solve exactly with the appropriate boundary conditions and negative times. So the first thing that one observes is that these whirl lines of the massless particles, they get shifts which are for functions of the heavy source, rho h, and furthermore, post the collision point, one finds that the motion along the x plus direction acquires an instantaneous shift along the x plus direction. So that's the theta function here. So that this is one effect. The other effect is that the impact parameter also gets correction. So there's a deflection which goes inwards towards the collision axis. So this point is explained. So this shift is explained pictorially in this picture here, where the shift is happening along the heavy shock. And the bending inwards is in the transverse plane. So that's this is something which which we have not shown here. Once we have the correction to these particle trajectories, one can plug that information back into the formula for the energy momentum tensor and extract the corrections to the energy momentum tensor, and then feed it back into the linearized Einstein's equations of motion. And once we do that, and after some rearrangement of these terms, one finds that the gravitational Lipato vortex, which Lipato originally computed using Feynman diagrams and using elasticity properties of scattering amplitudes, one can recover this by this classical analysis. So now we stare at these two solutions that we found in QCD and Gravity. So in QCD, we have this emission vertex, the solution for the gauge field, for the metric in the radiative spacetime. And in QCD, we have the solution for this gluon field in the radiative spacetime. And one can ask the question: is there a color kinematic type of relation between these two emission vertices? So we are not the first one to ask this question. I mean, this question has been asked previously by the authors, and certainly it seems that these vertices have the right color to kinematic factors associated to them. But the way this question was answered in these papers was using the version of the the way these people address this relation between the QCD Lipato vertex and the gravitational Lipato vertex was using the original BCJ color kinematic replacement rules. However, it turned out that in that procedure, one is not able to recover the gravitational Lipato vertex uniquely. What these authors found was that if you do those kind of, if you use the original BCJ replacement procedure, one just recovers the C nu part of the gravitational Lipato vertex. The N nu part was not able, they were not able to recover unless one adds some extra assumptions, like modifying the Yang-Mus Lagrangian by some contact terms, and those contact terms give additional terms in the scattering amplitude, and which then further gives rise to this bilinear here. However, it turns out that there's another way to find a to relate to find a relation between the QCD and the gravitational Lipato vertex, and it turns out that one needs to go sub-iconal in order to recover the gravitational Lipato vertex. So recall that in the QCD side, the way these vertices were obtained was by doing an iconal approximation. But if one goes on to sub-iconal level, meaning keeping terms which are of order 1 over p plus or 1 over p minus, which are not possible to obtain unless one has a detailed theory of sources, and then it's possible to find a different kinematic color kinematic replacement rule, which I will just show. So here, if you want, but before that, I should emphasize that in order to find the sub-iconal corrections, one would need a detailed theory of sources. So just like in the Einstein gravity calculation, where we had to invoke a point particle input, we had to supplement Einstein's equations with the geodesic equation. Likewise, in the QCD side, one has on top of the Yang-Mus equations the so-called Wong equations, which are which dictate the evolution of a color charge in the background of a slowly varying gauge field. So we have the usual Yang-Mus equations of motion, and on top of that we have these these Wong equations. So this analysis was done by Goldberger and Ridgway, and what we observed was that if we so what they did was to basically solve this set of equations to leading order in the gauge field for the radiation that that you produce when we have two color charges approaching each other, and they did the calculation in general kinematics. And if you take the ultra-relativistic limit of their formulas, one finds two kinds of terms. So the first term is the term which we already saw before. So this is the usual QCD Lipato vertex that one gets in universally in high energy scattering of color sources. But then there are sub-iconal corrections on top of that, which are 1 over P1 plus and 1 over P2 minus suppressed with respect to the top line here. And these corrections are known to be non-universal, meaning that they depend upon the particle spins and the interaction details. But for the Yang-Mills plus the Wong equations, this is the answer that they found. And the point is that if one invokes the following prescription, which was also given by Goldberger and Ridgway, where you replace each of the color charges by their corresponding momentum of that particle, and you replace this 3-point structure function FABC with its with the gluon 3-point vertex, this gamma nu1, nu2, nu3 with FABC is stripped off. Then this entire expression can be rearranged into a form which is exactly of the form that Lipatov found. So this is of the form C mu C nu minus N mu N nu. So we didn't have to do any thing by hand in order to recover this N mu N nu term. Now it turns out that when you do this calculation, there's an extra unphysical term that also appears here, which is proportional to K mu. However, this extra term, when you contract it with physical polarizations of the graviton, disappears from any computation of any physical quantity like cross sections and so on. So up to unphysical terms, this particular double copy prescription, which goes under the name of classical double copy. This is not the usual BCJ double copy. This is what Goldberg and Ridgway call classical double copy. One recovers this this gravitational Lipatov vortex. This connection between QCD and gravity that we found was is like one of the elementary building blocks of this 2 to n ladder, which will appear in BFKL and its nonlinear generalizations at the end of some long program. The fact that one can recover this kind of structure, complicated structure from a precise double copy relation of this sort, and gives us some roadmap as to what are the starting point data in QCD that we should look for. So in this case, we found that just the QCD Lipatov vortex is not enough. One also needs to have sub-iconal corrections to it in order to recover gravitational answers. So this brings to the end of my talk. So what we found, so the results that we found can then be used ultimately to compute the spectrum of gravitational radiation. And the work in this direction has been, in the case of Transplanckian scattering, has been done mostly by Venezian and collaborators. But they have been working in a regime where, which in our language is the so-called dilute regime, where the effect of multiple scatterings has not been taken care of. So then the result of this kind of analysis has the shortcoming that the very high frequency of this radiation spectrum cannot be reliably computed in the approximation that were used in these papers, and the way we would go forward is by doing the dilute the generalization of the dilute, which is the dilute dense calculation, and find if there's a double copy relation there. More generally, one would like to look for a color kinematic duality for amplitudes in Shockwave spacetime, and then computations of propagators to compute loops in the presence of Shockwave. So this point was very important in QCD, because it led to developments in this direction immensely facilitated the derivation of so-called Belinsky-Kovchikov equation, which neutralizes the BFKL Pomeron, and this is a nonlinear generalization of the BFKL equation, whose fixed point is the so-called color class condensate. So one question that we are asking is that does such an RG also exist in gravity, and can black hole formation be seen as a fixed point of this kind of renormalization group equation, which would be the exact analog of CGC being a fixed point of the Belinsky-Kovchikov equation. So with that, I thank you for your attention, and I can take any questions if there are.
Thank you, Himanshu. That was a very nice talk. But you know,
Can I ask a question?
please.
Yeah.
So in QCD there is sort of strong dynamics in the infrared, right?
Yes.
So that okay, this approach is working in some regime, but when we go the longer distances, okay, then confinement kicks in, right? Well, in gravity there is, well, not. There are some IR divergences, but they seem much weaker, and okay, there isn't like any dimensional transmutation, right? Coupling is irrelevant, so okay, in the UV it's strong, but in the IR it's sort of weak, right, by power counting. So does this play any role? I mean, is this
So at one loop still it's fine. But if you want to generalize beyond one loop, then there is like a pure Einstein gravity, we know, is not renormalizable beyond one loop.
Yes, it's just when like infrared dynamics seem very different, and yeah, especially when you go beyond 3 level, when you introduce like some loop corrections, like
right. So pure,
you say that differences are not important in this approach, or?
No, so pure one loop. Going beyond pure one loop corrections, one is something which I don't know how to do. But for example, computing things like the one loop Bridger trajectory is fine. One can use those building blocks to construct the 2-2-n ladder, and that would still be like a good amplitude. But beyond that, since we know that gravity is not renormalizable, so that part is something which I don't fully understand. Yeah.
Can I follow up with a really stupid question related to this? So in QCD, the beta function appears already at one loop. So already at one loop, you see that it's trying to get. In gravity, presumably this doesn't happen. So what is, should I just ignore this, or like how is this taken into account in this formalism?
So the beta function is already runs classically, right? So classically it's a dimension full quantity. So
yes, in gravity it runs classically, but the different opposite way to QCD, as Victor was just saying.
Yeah. So for example, if one is so before encountering like strong gravity regimes, one would expect some kind of a classicalization effect to happen, and like strong gravitational effects will be screened by a formation of a black hole.
Yes.
So if one like goes at smaller and smaller impact parameters, meaning that one is increasing the effective gravitational coupling larger and larger, then the effect of such a process will ultimately be cut off dynamically by the process itself, by the formation of a semi-classical state. So in that sense, one never kind of probes the UV directly. One first forms a semi-classical state, which is the black hole, and that kind of so this is something that one expectation like from classical physics, but one would like to see it as some kind of a dynamical process. So this is the RG that I'm talking about.
Could I also ask briefly, so do you have in mind some sort of analogy between black hole and proton, or is that we're sort of alluding to?
So at very high energies, this is the analogy that I was giving earlier, that if we boost a proton or any source of color to extremely high energy.
We know that proton has lots of soft whatever stuff, but I'm not sure you can think of a black hole as a bag filled with gravitons.
So if you boost a black hole to the speed of light in this very singular manner, where you take the mass of the black hole to 0, then you get a shock wave, which is the exact same thing that what happens in QCD. When we boost like a color charge to the speed of light, one can model that configuration to a very good approximation at very high energies with a shock wave. So the shock wave is the common feature in both the sites.
I guess there were attempts to model black holes as indeed in light cone frame, you can model them as some assembly of bits, and like in this matrix theory, there was, I don't know if you ever looked at these matrix theory papers.
I see. But yeah, so
Yeah, it was like trying to explain the entropy of a black hole in light cone frame using some guess of deep brains, roughly speaking, or bits. I don't, but just out of curiosity, you can look at.
Yeah,
like, I was co-author on some such papers back in '97, something like that.
okay.
With the Banks and Susskind, and yeah, it's like very phenomenological attempts of entropy using
Right.
this highly boosted frame, light cone frame, essentially.
Naively, the difference seems to be that in gravity, at like very long distances, when we know that classical physics dominates, right? If you have a large black hole, then okay, it's kind of classical physics. While in QCD, at long distances, we believe like quantum effects are very important, right? So just solving classical Yang-Mills equation of motion in some sense at long distances shouldn't give a good approximation, right? There's a confinement and it's kind of quantum effect. So naively, that seems the difference. Like QCD seems harder than gravity.
Right. Although to explain the entropy of Schwarzschild black hole, like no one truly knows how to do this. And
yeah. So and actually, if you so that's another disconnect from the shockwave description, because the entropy of a shockwave I would think that's like order 1 or something. It wouldn't be as close to like remotely close to a black hole at all. So that's another like a disconnect. But then again, I mean, the fact that one is able to recover things like the effective emission vertex is pointing towards the direction that there might be some systematic way of starting with the high energy configuration from the beginning, and then like doing a systematic 1/RS expansion.
Right.
And the question is what happens when the B impact parameter becomes of the order of RS, which is where we expect to form a like a black hole on classical arguments.
Okay. Well, thank you.
Thanks again.
Thank you.
Okay, great. Well, thanks everybody for connecting. Hope to see you in some venue soon.
Right. Hopefully in the new year. Right.
Holidays, happy holidays.
Yeah, happy holiday.
Grisha, are you still here?
Yeah.
I wanted to remind Grisha to reply to the. Oh,
yeah,
Grisha.
Here.
Yeah, I wanted to remind you to reply to the poll.
I mean, I'm still trying to wait
okay.
if I can apply for a visa. That's the problem.
The Schengen visa. Do you need any help with this?